Hello, everyone. This is Lisa Smith with Intel Corporation. We are here today for one of our webinars as part of the Intel Parallel Compute Center program. This particular webinar series is focused on advanced parallel programming, around more explicitly focused on exploiting multi-level parallelism in HPC applications. It will be facilitated by our very own John Kim, who's a senior application engineer. Throughout the presentation, you are more than welcome to submit questions. If you look on your right-hand navigation panel, it has a list there to where you could submit questions. We will answer those questions real time throughout the presentation. So without further ado, I welcome John Kim.
Thank you, Lisa. Good morning and good afternoon, everybody, or good evening. So this is John Kim at TCD. So before I start, I will briefly introduce myself. So can everybody hear me well? Am I speaking loud enough? Okay, so I'm an application engineer in Joe Colley's micro group. Joe started this webinar series, and Larry gave a good introductory talk about parallel programming in practice. And today I will follow up with his presentation with the specific examples of multi-level parallel algorithm in the applications. So my background is a scientist. I studied physics and the material science, but I have been a big user of HPC since my graduate school. So hopefully I can. So this is, before I start, I just want to give you the heads up about the upcoming webinars on the tools, related tools. So a lot of topics I'm going to talk about is not going to be covered in details, and I hope you can go to the webinars scheduled by DPD and also the IPC through May. So please pay attention to those. And then if you have any questions on specific tools and techniques, send us the questions, and we will try to address it during this session and also in the following sessions. So this is sort of description of all the data, the hardware I use to collect the data. And just to make a disclaimer that we did measure these internally at Intel by myself, and however, the code that is going to be available to everybody, we should be able to measure all these things we are going to talk about during the talk. So the outline of today's talk is, first I'd like to introduce a genetic code which represents a large class of electron structure codes, specifically in the plane wave basis set, to introduce the kind of problems many application developers will encounter and how we have to think about the solutions and how to implement it. And it is a very daunting task to discuss all these complicated applications. So I will be very specific about the goals, what we want to achieve through these examples. And main part of the talk is going to be discussing the performance of these core computation in these codes and how we can enhance the productivity of the application developers and also the users by realizing all the capacity we have on our multi and many core architectures. And so specific example I'm going to use is the DGEM examples and FFT, 3D FFT that occur very, very frequently in all these electronic structure code. And I will conclude. So just to, let's start by describing what kind of application I'm going to use throughout this presentation. Of course, this is just an example to introduce you the concept and also to show you how you can solve these problems, and so that you can think about the similar solution or similar approaches to your application. So this is just a mathematical representation about what these codes do. So the class of code I'm describing includes quantum espresso, VAS, and QBox, which you are very familiar with. Although the details are very, very complicated, and then each code will be like 100,000 to millions of lines of code, essentially what these codes are trying to do is the equation you are seeing on the top, just summing a lot of loops. So pay attention to the first loop about K, which which represents a Brillouin zone in the physical sense, but mathematically it's just some numbers with a weight determined by the particular K vector. And inside of for each K point, there is a double sum which goes through some numbers, and the little psi, which is indexed by K, which corresponds to the Brillouin zone, and also the band index I, is some sort of vector. And we are having some operation that operates on this vector, which is represented by some Hamiltonian operator. And there is another important numbers we have to compute, which is called overlap matrix, called S. So they are just the dot product of two large vectors. So mathematically, this is what we are going to do. However, the details are very complicated, of course, and just the simple multiplication of Hamiltonian to the wave function involves a lot of operations. And we can imagine the kind of computation it takes. So from the data parallelization perspective, traditionally everything is done in MPI. By recognizing the fact that K indexes are loosely coupled in the sense that although there is a coupling between different K points, they are essentially independent up to a point. Therefore, you can divide your multiple rows into multiple MPI groups for each K point. So each MPI group now is going to own a slab shown as a light thin rectangular box. And here we have a couple of dimensions. So we talked about K points which run through one direction. And there is a large number of bands we have to compute, which goes to the indices of I and J. And each vector now contains another 3D grid, which involves X and Y and Z directional grid. But so it means that in the computation we have to deal with this much data, and we will have to partition the data to be able to solve the problem. So big partition issue is about how to distribute the K points, and also how to distribute the number of bands we are going to compute, and also how we are going to represent the internal vector. So this is the setup we are going to use, and then just keep just focus on the loop structure we are going to serve. And also we want to understand what kind of problems we are going to solve with this kind of code, and what kind of characteristics. A couple of things that are very important to notice is that the number of K points varies from 1 to a few thousand. And in some cases, it can run all the way to 10,000 or more. And there are also the quantity we will define as a number of band, total band, which is typically 100 to 10,000 for this kind of a problem. And the other important parameter is, of course, the dimension of the vector we are going to serve, which is represent the FFT grid in 3D. And they are typically 100 to thousands. So this is the ballpark of the parameters we are going to use. And another thing is about the characteristic of these variables. Typically, the number of total bands is proportional to the grid size. So the bigger the grid size, we tend to solve a much bigger problem. That's important to notice. And when the number of bands is very high, we tend to also use much less K points. And there are complex or complex 3 or FFT to be used. And because we are relying on FFT to do this computation, double precision is necessary. Although there are some areas where probably the double precision is more than enough. Now it's just too much computations. But nevertheless, we are going to assume that we are going to serve the complex or complex 3 or FFT in double precision. So the reason why I brought up the characteristic is because it means that depending upon the problem, the number of K points and number of bands are going to change, which also dictates how you are going to distribute the data and how to compute, do the parallelization. So it means that the code should be able to handle this a wide range of parameters effectively for any cases. So what are the goals of this exercise? I mean, I'm not going to do real code because it's just a huge task. However, we are going to, our goal is essentially enabling these codes to do much bigger problems faster and better. And that's the goal. And we are going to use a very, very simplified concept to show the method that lead to that goal. So just a reminder, indeed, there are really a large fraction of HPC resources in the state and also in Europe and in Asia, everywhere, are consumed by these applications. It's really numerous and very critical in many areas of science, and indeed very computationally demanding. So how we are going to do it for the Xeon and Xeon Phi platforms of today and tomorrow. So we are not going to talk about just now how fast we can do these things, but we want to make sure that all the changes you are going to do and code design you will carry out should be applicable to the architectures of tomorrow too, hopefully. So we are going to focus on how to actually exploit multiple parallel opportunities in this application through hybrid programming. So the reason I went over the formula a little bit carefully was because you can immediately see the multiple ways to parallelize this method and how we are going to map that to the architecture. That's one thing we want to think about. And because of this dependency of different parameters, we want to be able to develop the adaptive parallel algorithm, not just the parallelizing in a specific way and hard-coded way. So we want to make sure that depending upon the problem and depending upon the platforms you are going to use, we should be able to make the application very adaptable. And we will implement that way. And definitely throughout the process, we should focus on how we can design the code so that we improve the portability and also performance portability.
Okay. We do have a question by John. What is the adaptive parallel algorithm?
So the one example is when you look at the formulation, we talked about number of K points and number of bands we are going to deal with. And because the parallelization, sort of the communication required between K points is much loose, it is definitely going to be just fine on MPI. However, you want to improve the performance on shared memory machines when the communication is very, very intense. It means that you should be able to choose any number of MPI and OpenMP threads depending upon the problems you are going to solve, and also depending upon what kind of processor you are going to use. You will have a different solution for the Xeon, the fat core versus my system. However, the code itself should not be different. It's just how you are going to change your parameters and how to optimize the runs. So that's what I mean by adaptive. So just a reminder of what we need to do before doing anything about the application. We just have to remember these three axes we talked about last time about MPI that is really designed for the distributed computing, and OpenMP for the shared memory. And we now have the SIMD dimension, which really critically changed the performance of it. So SIMD is sort of a given. We can't do much about it because it's dictated by the architecture we are going to work on. However, we do have a very much of freedom to choose between MPI and OpenMP. So when I say adaptive means we should be able to change our runtime between different combination of OpenMP and MPI to be able to use the memory the most efficient way, and also the way to reduce communication overhead if there are many. In any cases, what we have to remember is what the cost of moving data, and we should make sure that all these data partitions and algorithms should take into account the fact that the moving data between node to node is quite different from SIMD lanes. It means that your algorithm and implementation should consider these factors in a very careful way. However, being adaptive means you shouldn't focus on individual components of the layers, but we just make the overall structure so that we can be very adaptive. And each parallel level, whether it is MPI or OpenMP, we just have to make sure that we follow this basic principle of parallelism, parallel programming, looking at enough parallelism we want to do, and the optimize the granularity and all that. So keeping this in mind, and this is going to be some of the reminder about OpenMP we are going to use in addition to MPI. So throughout the talk, I'm going to assume that MPI is given. You are going to use MPI one way or the other to be able to deal with the clusters of multi-node. And of course, you might be using PGAS language, but nevertheless, you are going to exchange the data in this case. So we have the programming model for the cluster to deal with a group of computers. And now we do have a core processor and accelerator within a node, and sometimes we have to think about the communication between those two. So specifically on with the current mic generations, K and C. And within the node, so we have a node which just a collection of sockets and cores, and depending upon the platform we are going to use, there are different combinations to different configuration that makes up a node. So MPI was traditionally able to cover from all the way from cluster to core so far. However, because now each core is getting, and there are way more cores per socket or node, and also we have to handle the multiple threads per core. So how do we do? So traditional MPI has some limitation and also some overhead that is involved to handle the MPI on this at this scale. So OpenMP provides the very flexible and also very effective programming model to handle the level of parallel programming within the node. So there are, the OpenMP standard has been around since 1990, late 1990s. So, and there has been additions to the standard over the years, and specifically OpenMP 4 introduced a very important concept that affects the performance on the current architectures. One example is about how OpenMP 4.0 on the SIMD directive, which concerns really the SIMD direction we talked about. The other one is, of course, because of the introduction of the co-processors and accelerator, OpenMP now have the directives to handle the devices or targets. But more importantly to this talk today, there are very useful tools that define OpenMP 4.0 about affinity, which concerns the node all the way to the hyperthread. So why is this so important? Because OpenMP was introduced as a programming model for shared memory machine, which means that you shouldn't be thinking about where the data goes and how data is allocated and so on. However, now with the introduction of this kind of multi-component, hierarchical components, where OpenMP thread runs and how data is managed is quite important, particularly for the high-performance parallel programming. So these are the affinity tools we are going to take advantage of to be able to get the performance with OpenMP. So let's go back to our initial problem, the plane wave code. So the whole mathematical expression is reduced into this simple line of code. So remember that we had a k point. So that's just some distribution of MPI with a very, very little communication. So we are going to remove that part and assume that we are going to handle only one MPI group. And within an MPI group, now we have a multiple MPI task. And in this particular example, I took, let's take 512 and then total, and we have some MPI tasks. So each task will have number of bands, and I'm going to even assume that it is evenly dividable. And we have an abstraction about the whole vector, how we are going to represent. So within an MPI task, we have a very, very simple structure. And the computation of the double loop, which within for K point now is reduced to just the sum of looping over I, which is simple, and we will do a lot of things. However, within that, if for each band you do FFT on the vectors, we will do some computation in inverse FFT, and so on. So just to represent the complicated computation you have to carry out to do that, the mathematical representation we show. And we should have to do some MPI, because otherwise why would you use it? If we don't do any MPI communication, it means it's a very embarrassing or trivial case. We are not particularly interested. However, so this is the basic structure. So what does the compute Z or R look like? What do they look like? It's going to be encapsulating the sum about J. So we have I'm just making up, very simple cases. However, it is very representative in that we are going to compute the overlap, which is a dot product of a vector I versus everybody else. And we are going to do some operation for which has a different loop variable, but do more. It could be GEM or GEMB and many complicated user code. So this is a typical, so how complicated it is will depend on the method it is going to each code used. But nevertheless, we can represent our computation in a very simple sense. And then when you look at this one, so we already took care of the MPI parallelization. And now we are going to think, so how we are going to improve the performance on a shared memory machine. And by realizing the fact that the operations per band is largely independent from the rest of the code, and then also the other loops, it can be carried out very independent way. So it means that obviously the easiest thing we can think about to do is enabling parallel using OpenMP to do the parallelizing. So we will do the parallel 4 over the band, and FFT could be running using a threaded MPI, the threaded FFT, and computation now has another layer of parallelization we can explore. So what OpenMP gives us is to be able to do this kind of incremental incremental parallelization without really seriously restructuring the code. However, one thing I decided to do differently from the other OpenMP parallelization you might have seen is that instead of just to rely on FFT parallelization, the parallelization of FFT or the lower level compute Z, we recognize the fact that the index I is also quite independent. It means that we can do much bigger chunk of the parallel work at the upper level, and we can refine it for the second level. So this is sort of the nested OpenMP that is what's possible through since the 3.0 standard. And furthermore, now with the good compiler compilers and also runtime, we are able to run this kind of nested OpenMP very effectively. So but on the other, but what we are going to talk about the rest of the talk is about, can we really do it, and what is the predictable performance when you do this kind of operation. And hopefully I can convince you that this is a possibility you can explore in your applications as well. So how to increase the performance? Let's define the performance as well. So we want to definitely minimize the time to solution through optimization, and also by adding more thread and adding more parallelization. But what is important as well is the sustained throughput. Means if you are you can improve the time to solution to some degree, but if you are not able to do as many simulations as you'd like, that might not be the best solution. So the best outcome will be to do both. We do solve the problem as quickly as possible, but at the same time, we do as many simulations as we can do. And the key, of course, is that exploiting shared memory. So one thing I didn't bring up during the discussion is why even we are thinking about MPI, OpenMP parallelization with this code. Because if it is a very well parallelized MPI code, very seldom you will, the gain is very minimum, very often. So in a way, the restructuring of the code to utilize them doesn't make sense. However, in this class of application, there are a very good incentive to do so. It turned out because of the nature of the sum, which involves everybody, means that there are a lot of communication. Basically, everybody has to know everybody else. At some point, you have to do communication one way or the other. In particular, partition I adopted was breaking up the bands into the MPI task, which means at some stage, all bands have to be rotated or visited to the other MPI task. So it means that there is a large data transfer. So by using the shared memory programming OpenMP, it means that you can optimize that data transfer. First of all, instead of transferring to many MPI tests to many MPI, we can reduce that to be fewer MPI. And also, so typically you will see that in this application, more than 20% is being spent on MPI communication, even on large scale. So that's a serious one, and definitely that's the area we can improve the performance by just not doing the communication and not sending as many data sets as possible as we are doing. And the other key is, these codes are not just doing one thing. There are many levels of theory they are implementing, and very often those methods require much higher memory. It has much more memory requirements. It means that dividing the node into many of MPI has a lot more overhead than the simple method. So being able to take advantage of the large shared memory on the node is very essential. And of course, in addition, it means that we should be able to exploit also the highly optimized libraries in OpenMP runtime. For instance, FFT, nobody's going to, everybody can write a 3D FFT by own, but you will quickly realize that the libraries are doing so much better. So we should be able to take advantage of that. And of course, the GEM is another example. Large operations are highly optimized and very optimized with the thread as well. It means that we should be able to take advantage of these things without taking the hit with the MPI overhead. So just these two facts that, yes, the shared memory, use of it will increase the performance through the reducing the MPI communication overhead, and also because we can take advantage of the libraries, we should explore this one. And I want to be able to show that indeed these combining different libraries and user code with OpenMP indeed will be able to provide a sustained throughput while minimizing the time to solution.
So John, just another question. Are there areas in which or examples we should avoid when we're looking at increasing the performance?
Can you rephrase the question?
So you gave a lot of examples around how we can actually increase the performance. Are there areas in which our perception out there that we should avoid when we're looking at that?
I would say probably not. I think there are always ways to improve it. So, so I'd like to think about the possible cases, but I think in general, with all these applications and algorithms have a very, unless your application is seriously serious, that means there's no chance of parallelizing it. That's the only thing, but I don't think any scientific applications have that obvious disadvantage. So I would say be brave and explore all the possibilities.
Another question came in for Fiona. How do we handle codes with a very flat profile? These types of codes need OpenMP adding to the whole code, which is not trivial.
Indeed. So in fact, I reduced this very complicated cases down to very simple lines of code. So that's a big problem. So it's a flat profile is one thing, but you are probably concerned about the profile with many hotspots with a very equal weight. So that is a big problem. And in fact, I had a presentation on how to deal with that kind of a situation at NERSC. So, but the key is you just have to decide the entry point. Even though you have many profile, many hotspots and many routines you may think about or you may have to touch, but there will be a good entry point at which the adding OpenMP parallelization will have a maximum impact. So how to determine that is a highly problem dependent and situation dependent, but there are some patterns we can extract from these applications, and I can go into details later on, offline, and then I can discuss and show some examples of that.
Yep. And Fiona, I can send you the link or send out to the team the link to the NERSC webinar. I believe that's going to be posted. John just actually facilitated that just a couple days ago.
So going back to our simplified code, even the very simple things you can do will improve the OpenMP performance. Just a reminder of how important it is to do the right thing. So we talked about adding additional. So for the question regarding the question, so obviously you will start from this kind of parallelization on the left, meaning yes, it is nice to be able to attack the really root of the parallelization of the most effective parallel routines over the outer loop, but in fact you do discover the fact that you can do the parallelization within the small routines. So you may find this compute G as one of the 1 out of 5 routines, then you will start with this one. So what the nested OpenMP and OpenMP in general provide you with is this fact that you can start really one by one. And very often, something like this one, which is typically the target OpenMP parallelization routines, can be incorporated as the lower level of OpenMP later on. So even though you have a big code to work with, you start from sort of the big, small, big at the same time, lower level, and move up. And at some point, the effectiveness of that method is limited, and you may have to go from the other side in that you start from the upper level and try to change the code accordingly. But the key is you can do both in an incremental way to attack your problem. So just going back to the example, so one, while you are doing all this parallelization, you will make sure that you do the best thing you can do with the OpenMP parallelization, keeping in mind the principles of good parallel programming. Do not synchronize if you don't have to. Do not kill the thread if you don't have to, and so on. So I'm assuming that these things are happening without being told. So how am I going to predict the performance of this genetic electronic structure code? So basically, we are going to use simple compute Z or compute the FFT to predict the performance. And the key question we are going to ask is adaptability. We talked about MPI and OpenMP and arbitrary selection of those number of MPI tasks and OpenMP threads depending upon the problem. So can we actually do that? And what is the consequence of doing that? and all the runtimes and compilers are able to handle those things. So we want to make sure that indeed that's what you can do, and this is the kind of this is the simple code I use to be able to predict that yes, that's a possibility, or maybe it turned out that you have to do only MPI depending upon the architecture. But the key is, we can characterize what kind of performance we are going to obtain on various architectures, specifically into Xeon Phi, and then just to show, the flexibility you have from the programming model with a hybrid MPI and OpenMP programming with many nested ways. So don't forget that, the MPI has a fantastic feature of dividing MPI into multiple groups. So already we took care of one level of parallelization over K through the MPI task partition. And within MPI now, we are going to introduce additional partition, which concerns the number of bands we are going to talk about, the outer index. And internal computation will be further parallelized through the nested OpenMP and add the performance in the sense that the shorter time to solution while keeping the throughput constant. So the experiment I'm going to show you is this one. So in a way, what I'm suggesting through this presentation is for you to do similar experiment with your computational kernel and decide what is the best strategy for your application, depending upon the runtime and also the platform you're going to use. So I'm going to substitute the compute with the DGM in various size and also with FFT. The key thing is about this also approach is that what is compute can be is very, very open. You can decide the unit of the computation, which can combine also DGM and 3D FFT internally, or it could have a very complicated user code. But what you are deciding is the level of parallelization we are going to adopt at the higher level, and they allow another level of parallelization to take advantage of the architecture. So the test is done by varying the MPI test and OpenMP threads, which concerns how you distribute the band. So the model we are using is we have a fixed number of bands per MPI test. So every MPI is doing the same thing on different data. That's the data parallelization. And of course, OpenMP now is working on the bands you own, each MPI own in parallel, and each band operation is further parallelized by NKL. So we now have 3 parameters we can change. So it's a lot of parameters, and some people don't like that. However, I would say your applications are already very complicated, and in fact, by not using these different properties wisely, will paralyze you. Yeah. So either you do 1 calculation versus 10 calculations. So, so in that sense, I think thinking this complicated case once will be useful because the outcome will be very great. So on KNC, I will choose the total number to be 60 all the way to 240 because I'm using the 61-core KNC. Hardware architecture, CPUs, we are going to use either 28 or 56. That is the number of cores, a 20-core 2-socket machine. So how we measure the performance, we are going to just measure the total flops per second for DGM because there is a standard formula. And 3D FFT, I'm going to use the number of FFTs per second as a measure. So what is not going to be discussed extensively here is about other type of computation you can do in this particular application. For instance, FFT, I assume that the whole vector is residing within an MPI, so therefore there is no need to communicate between MPI tests. However, there are some plane wave codes which adopt the parallel FFT. So it means that now not only the bands are distributed, you may have you may distribute the vector on MPI. So that brings up very interesting questions. So, and I've been asked about this question quite often. So, what would you recommend? So, I think I want to just make you think about what we have now. So, many of these plane wave codes have adopted the parallel FFT over MPI test because it was written in the era when there was no big shared memory node. So each node was like less than a core of today. So it means that what had to be done at the time is going to be not necessary or essential. It could be also penalizing. So I will add some comparison of the cluster FFT and threaded FFT so that you have some sense of what to do in this case. And you will have a very similar situation with the other algorithm as well. And of course, I'm ignoring the SIMD throughout the application because I'm using DGM and FFT highly optimized through the MKL library and some other issues. And also, you can consider, looking at other new features like MPI3 shared memory optimization and non-blocking collectives to optimize the performance of these applications. So there are many things we can do, but fundamental thing we have to do is to recognize how we can take advantage of the parallelism in the application in a most natural way and the most effective way. So DGM, so from now on, I'm just going to show you some numbers just to give you some idea of what you expect when you have a MPI and OpenMP over the band, and also utilizing the threads for the MKL routines such as DGM. So imagine you replacing your own application code with DGM, so you will have a very similar experience. So this is sort of, so here I want to introduce you a very important concept you want to use in order to actually perform very well with the nested OpenMP. So the first, on the right, you see the environment I'm using to be able to do this experiment. First of all, we have to make sure the default of OpenMP nested is false. It means that it will always assume to be 1, the internal, the lower level OpenMP thread. And we want to make sure that actually you can take advantage of nested OpenMP. It means that, when you say 60 and 4, so the OpenMP nested has to be set to be true. At MKL, you also have to make sure that it doesn't reset the threads based on the fact that DGM is called within OpenMP region. So there is a basic things you have to say in order to exercise the OpenMP nested nature. And the second group, which is called OpenMP num threads and OMP proc bound, those are the two OpenMP 4.0 affinity feature that it was introduced. So it means that we are telling the runtime how to distribute the threads. So, first of all, we have a upper level thread which corresponds to the number of the OpenMP over the band, and the next one, in this case, we are going to fix it to be 4. So all the computation is done using 4 threads, which means that the 4 hardware threads per core is taking advantage of the core, and then number of OMP will vary depending upon how many MPI. So the graph shows the distribution. So what is the total gigaflop we can obtain through this example, depending upon the problem size? As you can see that regardless, there is hardly, there are some changes. Obviously you can see that for n equal 512, pure MPI using 60 MPI versus 1 OpenMP seems to give you better performance than using 60 OpenMP versus 1 MPI, even though we didn't do anything about the communication. But the change, the variation is very negligible. It means that you can just pick and choose. That's the adaptability we come back to. So you can choose, depending upon your memory requirement, you will choose different number of MPI, and then you will choose the best number of OpenMP. Okay.
We have a question from John. How about the results? How about the results in the case of N? Is not the power of 2?
Oh, it's very similar. In fact, so in fact, I'm showing you power of 2, but there is a total gigaflop is going to be very similar, and it's very independent. First of all, the OpenMP layer shouldn't care about what the size is. It's just about how many concurrent DGEM is going code. And then the performance of each DGEM will depend on the problem size. But if it is a bigger problem, the dependency is very weak. So we are achieving almost like 80 to 90% of the peak for the problem size around 1,000. And here is some examples. So how about the time to solution problem? So how can we improve the time to solution? So of course you can use many nodes, but this experiment is limited by using just one KNC car. So I'm not. So but let's assume that we can use many cars. But what we can do is now we can use more MKS threads to speed up the DGEM. And here is the change you will see. So we have the same number of N. So now we are going to change open MKL threads before all the way to 16. And we will change the MPI, number of MPI task and OMP to fit to the total number of threads we have, 240. So that's why they look somewhat different. But the good news is indeed each DGEM is taking much less. It means that for certain problems, you can just use more threads to do the DGEM and then use less number of OpenMP and MPI and change all that. So on the right, I'm showing you the case. So now because I established that the combination of OpenMP and MPI is really, you can pretty much choose anything. So are we going to pick the number of MPI to be 3, and then just to change the number of OMP? And then, of course, that means the MKR is changing. As you can see, so it's a lot of data. I know you have to proceed, but the key is in any combination, the performance fluctuation is quite minimum. It means that you will be really choosing the best performance you want to get, either to optimize the flops or you can optimize the time to solution. And this is just the fact that people ask what about hyper-threading in 1 or 2. So in fact don't worry, you can just use it and just use all the threads you have. And one example is that so I guess this is the example you are looking for. So yes, if you choose 600, which is not part of 2, still the performance is close to the 80% of the peak performance. So in fact you just establish the fact. And what about the house? Well, it's a rather boring picture because they look good. So it's good. So we want to make sure that what we are going to do really doesn't do any harm. We want to improve it, but at the same time, we want to make sure that we don't do anything worse than before. So definitely, it's the same story on house. A rather boring picture. And in fact, if you do the strong scaling of MKL, it's a bit less optimal in the sense that for small problem, definitely you are seeing the performance degradation when you use more MKL threads. But for the big problem, of course, there is no difference whatsoever. So it will be really depending upon the problem size you are going to solve. So FFT, so it's going to be a very similar experiment just to establish. So FFT is chosen just because it's so important in this course and also in many applications. And the users should be able to choose between the FFT over the nodes versus FFT within the node using thread. So in this case, number of the threads, MKR threads, will be quite critical. And there are a lot of the knobs we have to change with the FFT. You will see that a lot of applications have been using FFTW in many because of the portability and also because it's a performance on various platforms. So MKL does support the FFTW wrapper, and so you should be able to use it without changing your code. But there are some caveats you want to pay attention if you are using the with the FFT in a way I'm showing you here, because we are doing multiple FFT and each FFT is threaded. So it's a lot of threads and different levels of thread going on. It means we want to make sure that we set it is prepared the FFT to be able to do this calculation as well. So one option is, of course, the FFT can handle multiple FFTs concurrently. What it means is that we talked about using the loop, outer loop, which performs FFT over the band. However, you can imagine doing all those bands together with FFT. So that's one option. But it turned out, because of the data layout we have to deal with, and also because of that, turned out the multiple FFT simultaneous one through MKL is not optimal. But those things are also something you can change based on your application. So FFT, pretty similar story. So here I'm going to show you the 3D FFT on KNC, the size of a 64-cube problem. So here I want to show the FFT parallel efficiency again, the time to solution issues. Can we push can we choose a different number of threads for FFT while keeping the throughput constant? In fact, I think for a wide range of the MKS threads and OpenMP, you are able to do that. So the parallel efficiency, in a way, is the fact that it follows the ideal parallel efficiency is good. It means that we don't, yes, there will be penalty when you go all the way to when you use many threads for FFT. However, that means that you are going to be able to solve the problem faster, so you can use much more nodes. So that's good. And the throughput is pretty much insensitive to whatever the combination you are going to use. So this should be encouraging for you to think about really making the adaptable parallel program. And then the bigger problem, of course, the parallel efficiency is always better, and you will even see the better super scaling, quote unquote, in some sizes. And the story is simple, that we can indeed obtain both parallel efficiency and also throughput. So back to some questions that I brought up, and also some people brought up, was about, what about using MPI FFT versus a threaded FFT, so because our code is written in such a way. So this is just to give you some idea of what the advantage of the shared memory program has over the cluster MPI, because FFT, if you know about the internal, it involves a lot of data transfer. So basically, in all implementation, there is some sort of all-to-all type of communication to be able to handle the FFT. So that has to be done because it is a distributed memory programming model. So, however, what is the cost of that compared to the on-node on-node FFT? So this is an example on KNC. As you can see, so here the x-axis is either MPI task for the cluster FFT or the MPI number of threads. The good news, both of them, is that they do scale pretty well. And also the throughput is pretty constant. There isn't much of a hit because of you are using more MPI for parallelism. But as you can see, the performance is quite strikingly different. I mean, one could imagine that maybe MKL FFT is so much worse, but I somehow doubt that. So it is really the exposing the cost of data transfers between the nodes when you strictly apply the distributed programming model within MPI. So just the news again is, I'm repeating the story over and over again, in that you have really many tools, many knobs. Yes. So rather than thinking, oh, there are too many knobs, I don't know what to do, just to think differently. Oh, we have so many knobs we can take advantage of and actually enhance the performance to maximum. For instance, depending upon the problem, we will just do different things. And then, so you should be able to carry out similar experiments at a micro kernel level, but put together at the end for your application. So about the similar stories emerged from Haswell, in fact. So I'm comparing you the cluster FFT with the threaded FFT on Haswell. As you can see, they do, all of them seems to be working as expected, but the key is that, in fact, using pure MPI to, so the CFFT does perform about 1/4 of the threaded MKR. So what it means is, yes, the cluster FFT will scale, so you can use more nodes. But that means that you are using more resources to do exactly the same amount of computation. So it's the kind of decision you are going to make to optimize your resources. And there is some other plot I showed you, but there is so all these things will be posted. And if you have any questions about how to do the similar experiment, I will help you out. So what does that mean, or what do all this mean to us? Going back to our initial goal was that, in fact, we have a really flexibilities in choosing data decomposition with MPI and OpenMP, because the two programming models offer very different, have a very different characteristic. MPI start with a distributed data. The structure means that you don't own everybody, versus shared memory model, you own a lot of things together. So of course, there are implications on how to do OpenMP to make sure to optimize the performance. But those two things are quite important factor, and how to take advantage of that for your application will be important. However, good news is, you can pretty much decompose your problem to do the best you can do on any situation. And nested OpenMP, as you saw it, and then give you the better time to solution. And we didn't do anything to do that, because just we took advantage of the good libraries that are available to us. And we can get the higher total performance and also the resource utilization. And definitely the big gain in memory with less MPI tests, which is not important in this example because we are just using one node and the memory footprint is the same. But it will be quite critical in many other methods these codes are going to be used, such as the GW. Yes.
And a question from John. How about hybriding OpenMP, SIMD? Any suggestions or advice?
Oh, I assume that is done already here in this case. So, for instance, the FFT, the data structure to do FFT should guarantee the vectorization already. And I think that is somewhat orthogonal to the discussion we are having. So what we are saying is parallelism in the algorithm sense can be done in a way we discussed today. And the vectorization will be just the axis that we carry out all the time. And we just to make sure that the data structure is already always amenable to the vectorization. But that's sort of two axes we have to do. And I'm assuming that can be done. And there are some other optimization we can imagine to do. And the allocators can be highly optimized to with the particular data size and the architecture. And all these things have to be done carefully so that we can actually do the MPI work as well as we used to do. And key is that it works for both Xeon Xeon Phi, as I showed in the data, and it will work on any CPU architecture. But again, I think what is important to think is we have flexible tools and we have very powerful tools, and you can use it and very productive way. But you have to think about actually good data acquisition and also the parallel algorithm, rather than just thinking just put the OpenMP here and there. But think a little bit higher level to see what parallel algorithm you have, and then try to do that as well as you do. And the tools are there for you, and I think that's the good news. Thank you for your attention.
Okay. Thank you, Janam. Great information. I'm hoping that a lot of you have gotten a lot of good information to go back and try some new techniques with your code. That concludes our webinar for today. There will be a short survey concluding this webinar. If you could fill that out and give us some feedback, we'd greatly appreciate it. And thanks, everyone, for attending. Look forward to the next series of webinars. Again, they're going to be focused on techniques, tools, using different use cases that we have coming up. So please definitely register for those events coming up soon. Thank you.